Welcome to a moment of seismology and tectonics, where I share one story from a published scientific article every week. The Earth is composed of multiple layers. The outermost shell is relatively rigid. This rigid shell consists of multiple blocks. We call them tectonic plates. I'm currently sitting on top of the North American plate. In geology, we call the relatively stable continental cores cretons. Cretons are usually underlain by volumes of mantle materials that are melt depleted, strong, buoyant, and diamond rich. These are mantle volumes underlying cretons are called mantle queues. Mantle queues often demonstrate layering structures. They were formed only in the early Earth's history more than 1.5 billion years ago, without modern analogs. Understanding the process that formed these cretonic queues has significant implications on our understanding of the tectonics of the early Earth. Using computer simulations, the authors investigated the formation of cretonic queues and the factors that may control the size and geometry of these layering structures. The authors set up the simulations with a model of oceanic subduction followed by the collision of oceanic arc and the continent. There is a pre-existing melt depleted mantle layer at the bottom of the downgoing oceanic plate. After the subduction began, they found that the depleted mantle layer, which is also hot and buoyant, was not able to subduct together with downgoing plate. Instead, this depleted mantle layer was detached from the oceanic plate and formed a proto-queue structure beneath the continental lithosphere that came after the subducting oceanic plate. With the development of the arc continental collision, the downgoing oceanic plate started to break off and left fragments of slabs within the mantle transition zone. With the consequent conductive cooling following the termination of a subduction, the proto-cretonic queue further developed into a cold, buoyant, and depleted cretonic queue that is observed today seismically beneath many cretonic lithospheres. The formation of the cretonic queues requires a mantle that is about 150 to 250 degrees Celsius hotter than modern Earth. This range of temperature anomalies also determines the size of the cretonic queue and the slab fragments that are stuck in the mantle transition zone. The findings in this study suggest that oceanic subductions with a highly depleted mantle in the early Earth are required to form the present-day thick, layered lithosphere beneath the cretons. This work by Alexei Perchuk and others was recently published on Nature. Please refer to the full article for more details. Thanks for watching this video, and I hope you enjoyed this very interesting paper. See you next week.